Actually, I want to start with the physical properties handout. Look at a couple of the back pages there. Again, tomorrow at 8:30, if you want to be here for just a little bit of office hours, group office hours time. 8:30 tomorrow and Tuesday. Physical properties. Also got this guy here. Okay. In many of my handouts, I'll include sort of miscellaneous things, just sort of applications, maybe just interest. The physical properties, we did not look at the last couple of pages. Crestor. You may have heard of Crestor if you watch TV. Most drugs act by binding to some receptor, like an enzyme. How do they bind? They bind by intermolecular forces, IMFs. And what are the four major types of IMFs? Well, we went over them, right? Hydrogen bonding is one important one, right? Okay? This is how molecules interact with each other, and how a drug will interact with an enzyme, which is a huge molecule. Okay? This is Crestor sitting inside. It's called the binding pocket. I don't know what they call it. They may not call it, but this is non-covalent bonding. IMFs are non-covalent. We're not saying that the molecule is bonded to the other one, but it's interacting by so-called non-covalent interactions. Those are your IMFs. Okay? So that's just terminology, right? Non-covalent. How is Crestor interacting with the enzyme? Well, the enzyme has lots of amino acids. Okay, it's a huge thing, but it has molecular components around. A lot of hydrogen bonding. Now, you got to be careful. Some people that draw these diagrams, I'm not so sure they know chemistry sometimes. Let's see what it looks like here. What are they trying to show here? They're trying to show a hydrogen bond. I mean, you got lone pairs here. We're not going to draw these H's out. You know, there's three H's. A nitrogen positive. But you see, we can get a hydrogen bond. The oxygen serving as the acceptor and the NH being the donor. Yeah. So, and every one of these IMFs is like glue, or like you know, Velcro, sticking this molecule together with the enzyme. All this hydrogen bonding around here. But look, this is where I wonder if people, they didn't know what they're doing. It looks like they're having an oxygen, sort of interacting with an oxygen. What is that? Two acceptors interacting? That's not true, right? So you got to kind of know what you're looking at here. I mean, this doesn't make sense. But we do have the H here, and we can maybe draw it like that. Right? Acceptor and donor.
I think that H is going up to the oxygen above it.
Yeah, and then this H, okay, I see what you mean. Well, then what's going this way? There's no H there, so if we do this, that makes sense. What's going over here? Well, I can draw this H out like this and have it coming this way. But right. Again, this is one of those things where a beginning student would look at this and be like, oh, no, that makes sense. Because it isn't drawn too correctly. The big idea is correct. We're looking at types of IMFs that can occur between the drug and the receptor. What other types do we see? Actually, what is this here? Yes, it could be hydrogen bonding, but it's also sort of what?
Dipole.
Well, yeah, they're all about the same, but it's particularly the fourth one. What was the fourth one? Ions. Ionic attraction. See, this is in the ionic state. It's minus, and that's a positive. So maybe you could describe it as hydrogen bonding there, potassium. It's also maybe an ionic attraction, right? Which is a pretty strong one. That was the fourth one, the strongest. What do we see here? This is actually a hydrogen bond between an H and a fluorine lone pair. Okay, right? Can fluorine be a hydrogen bond acceptor?
Yes.
Right, yeah. Although there is some question about that in the literature, depending on the type of fluorine can hydrogen bond. What is a hydrophobic bond? Well, I call it a van der Waals attraction. What does hydrophobic mean to you? Hydrophobic. It doesn't like water. Non-polar. Those are typically, well, non-polar groups. For example, this. What type of group is that there? Polar or non-polar? Non-polar. It's just hydrocarbon. Okay? Well, these amino acids, if you know your amino acids, they all have like the same thing. They have hydrocarbon side chains. Can these interact in any way? How can they interact? By hydrogen bonding? No. Dipole-dipole? No. What's the only way they can interact? By van der Waals, the weak type. The type that just sort of occurs by them just bumping in. It's real weak, but it is a little bit. Okay, so you see this? But again, it looks like the oxygen's hydrogen bonding with the oxygen. That's not right, is it? So the big point is there. Any questions about that diagram? Different IMFs holding that drug in place. And it's amazing, when you design a drug, you design it so all these things are in place and you can use molecular modeling. Design a drug. You do have to know what the receptor looks like. And maybe the reason it has this this hydrocarbon chain here is because I knew that there's lots of amino acids here with hydrocarbon. And you put hydrocarbon next to hydrocarbon. All you're going to get is this, but at least it's something. Down below, what is that, anatomy of a soap? What is soap typically? Most common soaps are fatty acids. Long hydrocarbon chain, which is going to be nonpolar. See, all that's nonpolar, just hydrocarbons. And that's called the hydrophobic portion, water hating. But you also have this polar so-called head group. And this is the carboxylic acid in the ionized state, ionic, and so it's polar. And so you have two regions. And that would be called what? Hydrophilic, water-loving. Because the polar is going to like polar water. So most soaps are like this. Why? First off, when you take a shower or something, you bathe in water or acetone? Water. So you got water there. So you want your soap to like water, but you also want your soap to like what?
Oils.
Grease and oils. Okay? Because a lot of times, you know, yes, dirt, but a lot of times you're washing off sort of oiliness. Okay? So this interacts with the oil, and this interacts with the water, and it all helps bring it together and make it kind of go together. If all your soap was polar, then it wouldn't like the grease. It wouldn't need to do anything with it. It would just avoid the grease. Okay? So you got sort of two, and this is typical soaps. If you ever look at your shampoo, next time you take a bath, next week, next whatever, it'll say something like sodium myristate or sodium palmitate. These are all long fatty acids. Hydrocarbon is often called fatty. Okay? And also, you can talk about this because the grease molecule, the fatty portions of the long chains can sort of coordinate with the grease molecule. But if it does like this, what's on the exterior of this sort of complex? The polar portions. And the polar portions can interact with the water. Okay? So that's typically what soaps are. Question over here. This is Nexium. Watch TV, you may have heard of that. I don't know, is that the one with the elephant or is that something else? I don't know. Nexium. Used for gastric upset, acid reflux, that thing. But Prilosec, is that still advertised, Prilosec, OTC or something? Yeah, something like that, okay. What's the difference in Prilosec and Nexium?
The name? I think one of them.
The name. So you could also say the cost, because there's a big difference in cost. Used to be. But what's the different structure in the structures? The only difference is here the nitrogen is protonated and it's neutral. Here it's deprotonated and it's the anion. How many lone pairs on this nitrogen? Yes, 2, right? That's the only way it would be negative. Because it's the conjugate base of that. Everybody can draw conjugate bases, right? Okay? That's the only difference. And so while Prilosec is an all-neutral molecule, Nexium is an anion. I mean, the molecule is an anion. Of course, it has a cation that goes with it. It's actually magnesium, so for every one of these, you got to have 2 of these. Okay? But it's the anion. Question?
The sulfur in the middle, what would the wedge, like how would that change how it interacts?
What do you mean the wedge?
There's a wedge on the one on the right and not on the left.
I don't see the wedge you're talking about. Oh, is it bolded there?
Yeah.
I can't really tell up there.
Or is it just a mixture?
I never really pay attention because I can't really see that up here. The sulfur is chiral. Another difference must be that Nexium is one stereoisomer. Once we get to chirality, because sulfoxides can be chiral. I've never noticed that before. I always focus in on this being an anion. Now that sort of takes away the punchline because you would say, well, first off, which is more soluble in water? Prilosec or Nexium?
Nexium.
Nexium, why?
It has a polar.
Well, it's got an ionic portion now. Right? Ionic is going to be, ions are better for water. Okay? Better in water. Yeah? More soluble in water. Now, Prilosec is older. Then they came out with Nexium. Why did they come out with Nexium?
I think that's the extended, like the all-day one.
Perhaps. There may be some other things. It also may be quicker acting. Why may it be quicker acting?
This is water.
Because it dissolves faster in the stomach, which is water. Right? Okay. But guess what? This is the kicker. When it dissolves, what's in the stomach?
Acid.
Acid, yes. And if you have H+, what's going to happen to this?
It's going to turn into Prilosec.
It's going to turn back into that. They charge a lot of money for that, but then as soon as it goes in the stomach, it goes back to this. Why do they charge a lot of money for this? Because this is back to not, you can get generic of this. Used to be you couldn't get generic of that. They have rights to it for like 7 years before generic can come out.
It's trickery.
But they claim that it may be faster acting, and that's how they can get a new patent. Because it will dissolve faster. But as soon as it dissolves, it's going to go back there. Okay, the big thing is ionic, though. The ionic version is going to be more soluble in water. Last thing here. I actually have color here. Solubility. Solubility. This compound up here at the top. Now, it has R groups on the nitrogen. The R groups have to be defined somewhere. To be defined. Defined below. If R equals methyl, you got 2 R's, and both are methyls. If both are methyl groups, the compound is called methyl red. Now, this is 2 phases. You have cyclohexane, which is just a hydrocarbon liquid. It's on top. I wish the yellow wasn't up there. It almost looks like 3 phases. It wasn't mixed well or something. Water below. Now it's called methyl red. That's because in the solid state it's red. But when you dissolve it, it's actually yellow. Okay? Which layer did this compound prefer? Water. You can tell by the color. It's more in the water layer. Okay? Now, does that make sense? Actually, no, because it's a neutral organic molecule, and we have said that neutral organics are going to prefer organic layer. The problem is cyclohexane is such a bad nonpolar solvent, but that compound has some polarity. It can hydrogen bond to water, etc. So that's a little bit odd there. Here's the main thing of the handout. What if we replace the R groups with ethyls? That is, we add more hydrocarbon to it. You see, it starts then wanting to go more into the organic layer. Because more hydrocarbon is going to start hating water. And if you replace the R groups, if you make them propyl groups, okay, this is the end here. This is where it's bonded. If you have two propyls, then it predominantly prefers the organic. The take home here is the more hydrocarbon you get, the more and more it's going to hate water and prefer the organic. Okay? This is a bit odd. Why does it prefer water so much? I don't like that because I want you to think that a neutral organic molecule is going to prefer organic. It's just cyclohexane is just such a non-polar organic. If instead of cyclohexane, if we had used like ethyl acetate, which still would give you two layers, I guarantee you a lot of this color here would be up there with ethyl acetate. So, the more hydrocarbon, the more it's going to hate water. We can look at the daily question here. This is ciprofloxacin in the middle. Is this guy over here going to be more soluble in water or less soluble in water than cipro? Less. Why less? The only difference is this. Instead of a 3-membered hydrocarbon ring, we got this, what, 7-membered hydrocarbon ring. More hydrocarbon. Going to hate water more. So it should be less soluble in water. What about the one on the right? More soluble in water or less? What's the difference?
No age.
Instead of this carboxylic acid, we've turned it into an ester, the ethyl group. Well, that's more hydrocarbon, so it's going to less soluble in water. Okay? Hydrocarbon is nonpolar. Would you call hydrocarbon hydrophilic or hydrophobic?
Hydrophobic.
Hydrophobic. There's terminology. Okay. Other coming up there is acid-base questions. Let's get to the acid-base handout. See where we left off there. Seems like we left off with hybridization question.
Is hydrophobic also considered lipophilic or no?
I didn't quite hear.
Hydrophobic, can you say that's also lipophilic or no?
Yes, we can say the term lipophilic. So lipid is like fat. Lipids and fats are nonpolar. So lipophilic would be the same as hydrophobic. Lipophilic. You rarely hear lipophobic. You never hear that. But lipophilic is a very common. Okay, it seems like we left with hybridization. Any questions what we've covered thus far? Any questions thus far? We've covered ways of determining how acidic a hydrogen is. and ultimately how acidic different compounds are. But we're going to focus in on the different hydrogens there. Okay, we're ready to look at bases. Bases is going to be the same considerations we had up there. Same exact considerations, but the ultimate answer is going to be reversed. Because there's a difference between an acid and a base. Let's look at it. Okay, what's the definition of, first off, in Gen Chem, what's the definition of a Bronsted lauric acid? What's the definition of an acid? Tell me acid. What's your definition of an acid?
Proton donor.
Proton donor. Have you ever heard that term? Proton donor? Well, I would encourage you to forget that term. Forget proton donor. That's the opposite of the way you want to think in organic. Okay? Yes, they donate proton, but I would say maybe more supplies to proton. Donate sounds like it's doing some action. No, the base is what does the action. Okay? Now, what's the definition of base you learned in Gen Chem?
Protonic subgroup.
See, it sounds like the acid is doing something, and the base is just sitting there accepting it.
So like the base, the proton taker.
Yes. It takes the proton. It takes the proton. It don't just accept it, it takes it. This is a terminology that's more important in organic because we use arrows. That's why I think most of you get your arrows backwards. Because you think it's supposed to donate it. It's donate. No. And the arrow is supposed to be used correctly. Bases take protons. They don't accept them. Okay? For example, here's an acid-base reaction. They're all the same. Any acid-base reaction has a base and an acid. Here, we got this and we got that. What's the most acidic H on the board? When I say on the board, I mean in the reaction. What's the most acidic H? H is on carbon or H is on oxygen? Here, yes. So there's your acid. So this must act as a base. Well, that makes sense. I mean, it has a lone pair. It's a carbanion. And here's your good old acid-base mechanism. These electrons take the H, they bond to the H, and what happens to these two electrons? They break away and they move on to the oxygen. That's our acid-base mechanism. So what is the outcome? The carbon is now bonded to the H. Right? Well, lo and behold, that's now methane. That's CH4. Okay? And then we created here what? Well, the arrow shows you what we create. This breaks away, third lone pair on the oxygen, and that's that. Same old mechanism. Okay? So here, this is acting as a base. Bases do need to have lone pairs in your standard Bronsted-Lowry, but we said that yesterday, right? And we said it when we did our acid-base mechanism. We've got to get used to pKa's, and we'll talk more about it in a little bit. pK of order 16, just like an alcohol. All right. pKa of methane is about 40. Some of this is just statements that aren't going to make a lot of sense in just stating it to you. But it's something to refer back to and make sure you understand these statements as we go along. Let's move down a little bit. Bases don't have to be an anion. Up there, the base was an anion. Here, the base is ammonia, a neutral base. But it does have a lone pair. And ammonia can take the H, the base can take the H, move that here, and you get what? Okay, this is a condensed. Condensed means it's kind of closer to formula. But of course, this is, there's your ammonia. The lone pair is now bonded to another H. And lo and behold, that's a positive charge, right? So there's your ammonium and hydroxide. And here are your pKa's that you might want to look back. Now, what's the last page of this? I don't know if I gave it to you. Sometimes I don't give it to you. Did I give you the no, the very last page. Yeah, miscellaneous points to remember. Okay, I decided to be nice and I gave you this page. Okay? Miscellaneous points to remember. One of the points to remember is that any acid-base reaction, you're going to have some charged species. That is, you're always going to have sort of a neutral, and then the other form is going to be an ion. See? Neutral, and then it goes to ion. Neutral, it goes to ion. Up here, it went from ion to what? From ion to neutral. Okay? That's your sort of, up there, that's the base of the conjugate acid. Okay? That's not something to memorize. I mean, memorizing it ain't going to do anything for it. It's something to recognize and just, as you develop your fuller knowledge of acid-base chemistry. Question?
I'm kind of confused why you draw the arrow to the H, but the H goes, like from the N to the H, but the H goes back to the NH3.
So it's like the,
Why do you want to say it goes? I think you want to say it goes because you want to say it donates. What this means, what does this arrow mean? By the way, on quizzes or tests, you'll get a WDAM. Okay? Whenever you draw, your arrow's wrong. This stands for what does arrow mean? And I'm like, I don't know what your arrow means. I'm like this. And beside it would be like -2 or something. I don't know what your arrow means. You need to know what your arrow means. This is supposed to indicate that the electrons are going and making a bond to H. And there's the resulting bond. We now have a fourth bond to H. See, these two electrons here used to be a lone pair. But now they have just bonded to the H, as illustrated by that arrow. Now this arrow, what does it mean? The electrons are moving away from that H and moving on to the oxygen as the third lone pair. This lone pair used to be bonded to that H. But the base took it, and the electrons didn't just disappear, they just reside on the oxygen. But we need to show that. A lot of people will not show this arrow. You need to show it. The electrons are just moving to reside on the oxygen instead of bonding to the H. And lo and behold, that's a negative.
It's kind of like the base is a bully and it comes in and steals the hydrogen and the
It
electrons
takes the
run
H.
away. The electrons are running away to hide.
Uh-huh.
I'm
I don't know. Those electrons are running away? Yeah, the
Yeah.
base takes the H. That's why I don't like the base accepts it, because then you don't know how to use arrows. It's opposite. Bases take the H's. Okay. For each pair, predict the strongest base. We did strongest acids before. Keep asking, okay? What's a stronger base, ammonia or methylamine? Which one's stronger? I'm sure in Gen Chem you learned what it takes to be a base, and you talked about base strength, right? Which one's stronger? Correct. Why is methylamine stronger?
I would think that the carbon, since it donates the electrons.
Ah, this carbon donates?
It's gonna
Because that's a standard tenet of organic chemistry, and sp3 carbon donates by induction. Donates electrons by induction. So, explain.
So it's going to make the electron density,
Thus, the electron density here, okay, if the electrons were like neon lights, you're pumping more electrons here, more electricity, and you're going to make the neon light bigger, glow brighter. Well, that's increasing the electron density, okay, where this guy is here. More electron density, it's going to be more attracted to this partial positive H. That is a partial positive H, right? That's why that guy is there. So the more negative here, the more it's going to be attracted to your H, and it will thus be a stronger base. Yes, that's a stronger base because of that inductive effect. Question?
When we say like the sp3 carbon is donating electrons, like it's not like not giving it more electrons, just like electron density, like.
I think it's the same thing. Giving you more electrons is, I'm increasing your electron density.
But like the lone, like we will still have one lone pair, right?
It's one lone pair, but you got to remember, these structures we draw are sort of limited. It's all this electrons here. The electrons can be perturbed. Just like shaking hands here, okay? I mean, the electrons don't have to just sit here, but they can be pulled one way. I can almost pull them all my way, then I'd become ionic. The electrons here, they're kind of pushed this way. And so it ends up being a little bit like this. And then there's more electrons here. You're wondering how this electrons contribute to the lone pair density.
So carbon has.
It gets complicated, and that's that book that's...
So carbon has more electrons that can be pulled than just a single hydrogen does.
Yes, you could look at it maybe that way. Ultimately, an sp3 carbon donates, and so we got that to invoke, and boom, increases the electron density. And there's a variety of ways you maybe can explain it. If the electrons come in here, well, ultimately, electrons do repel, even though they'll come together and make a bond. And so as you put electrons here, if you want to keep the ideas separately, putting electrons in causes this a higher energy because they're coming into the lone pair. The higher energy is going to make it want to go quench itself by getting closer to that H+. There's a variety of ways I could try to explain. Ultimately, sp3 carbon donates. Higher electron density is going to make it a stronger base. Next one, number 2. Which over here, which nitrogen is more basic? What argument can we make? Remember, we make the same arguments we made previously. There's 4 different types of arguments. What argument do you want to make here? The difference in the nitrogen here is a hybridization. This lone pair is in what type of orbital? Okay, this is sort of partially condensed. Of course, these H's are not bonded to that carbon. Right? You've got to get used to this. The H's are bonded to the nitrogen, and then the nitrogen is bonded to the CH3, right? Okay? It's partially condensed, mainly because it's just easier to write. So, what's the hybridization of the lone pairs in what type of orbital? sp3. It's the only type of orbital that nitrogen has. This lone pair is in what type of orbital? LP and sp2. Okay, which lone pair is going to be more reactive towards the proton? No, this guy. Okay. This is 33% S. This is 25% S. Which lone pair is held tighter to the nucleus?
Right.
sp2. Tighter to nucleus. Since it's held tighter to the nucleus, it doesn't get out there and react with protons. Okay, you're the proton. Here I am. You know, I got to move real close. That causes problems. Okay, what about lone pairs out here? I'm ready to go. It's almost like an electronegativity thing because same nitrogen, but we can say this. One of these nitrogens is a better parent of the lone pair. This nitrogen holds the lone pair tighter because it's in an orbital that's, right? This is it. And sp3 nitrogen tends to be fairly basic for a neutral atom. Indeed, if you look at the points to remember, it'll discuss what are good bases. Here we go. Good bases are usually anions. Anions, like hydroxide or that CH3 anion up here. Neutrals are usually not that strongly basic. Except for this. And sp3 nitrogen is a fairly good base, like ammonia. Because the nitrogen is not a great parent. And in the sp3 hybridization, not only is it not a good parent overall, the electrons are further away. And sp2 nitrogen has some basicity, but it's less basic. When you get to a sp lone pair, those are almost non-basic. So, good bases are anions or sp3 nitrogens, sometimes sp2. Now actually, in nature, a lot of sp3 nitrogen compounds act as bases. Okay, like we just said. If you flip the page, we'll see some of those. natural products that contain an sp3 nitrogen and sort of act as bases. And if it kind of acts as a base, these are called alkaloids. You're familiar with the term alkaloid? What does alkaloid mean? Oid. What's a humanoid? A robot can be kind of a humanoid, like human-like. Alkaloid is alkaline-like. What is alkaline? Basic. These are molecules that are kind of basic-like. Why are they basic-like? Why is this basic-like? Because of that nitrogen right there. It's an sp3 nitrogen. It's sort of basic-like. That's ergoline. It's found in some mushrooms. Now, a lot of these natural products are also have some interesting activities, like psychedelic activities. Here's LSD. LSD is actually an alkaloid because also alkaloids can be natural products. They come from nature. Does it have a basic nitrogen? Here's a question. Which nitrogen of LSD is basic? Oh, the basic one is the one with the lone pairs and an sp3. Which one is that? Top, middle, or bottom?
Middle.
Middle. sp3. That's your basic nitrogen. What type of orbital is this lone pair in?
P orbital.
Yes. P orbital. How about this one?
P orbital.
P orbital. Those are in p orbitals. Make sure you understand why. Here's a point to remember. Lone pairs in p orbitals are typically not basic because they're busy conjugating with the other p orbitals. Lone pairs in p orbitals are not basic. There's a couple of exceptions when the conjugation is not good. But that's the basic nitrogen. See, all these have a basic nitrogen, making them basic-like or alkaloid-like. LSD. Is nicotine on here at the bottom? Which nitrogen of nicotine is most basic? This lone pair is in what type of orbital? sp2. That lone pair, the sp2 lone pair is held tighter to the nitrogen nucleus. sp3 nitrogen is most basic. Okay, so those are alkaloids. Maybe you'll hear that term in biology or something, maybe in some interesting compounds there. Mother Nature makes amazing compounds that have lots of interesting activity. Including morphine. Yeah? Morphine's an alkaloid. Hey, those are beautiful molecules, yeah? Complex ring structures. But guess what? All of them have standard bonding. Carbon making 4 bonds. Nitrogen making 3 with a lone pair. Alkene. What is that right there? It's got a benzene ring in that one. Oh, what functional group is that? It's got an OH on it.
It's a phenol.
Got a phenol. What is this? It's an ether, an amine. That's just a plain alcohol because that's not aromatic. Okay, back to stronger. Next one, number 3. Got a whole bunch. We should already be able to answer this because we just told you. Which one's more basic? An sp3 lone pair, and this is a what? P orbital, right? Which one's more basic? sp3 nitrogen. Lone pairs in p orbitals typically not basic. Number 4. Which one's more basic? F minus or CO minus?
Is it the opposite of acids?
Kind of. Which one?
Fluorine.
Which one's more stable?
The most stable is F.
Yeah, right.
Most stable is which one? Who says F? Who says Cl? Cl is correct. Why? Because it's bigger. When we're in a group, size matters. Okay? Cl is most stable. So, which one is happy and not interested in protons and happy being like it's there? Which one is more wanting to go back to neutral? More stable is not going to want to grab the proton. It's very happy just sitting on the couch. It's very stable. This guy wants to go back to neutral because it's not as stable. So it will react with a proton, H plus is generic, some type of acid, to go back to what? Right, to go back to HF. It would rather be in the neutral. But that's just the opposite of coming, well, maybe it is, maybe it's not. But does that make sense? The more stable one is happy being minus. The other one wants to go back to neutral. F minus is more basic than Cl minus. F minus is actually sometimes used as a kind of a weak base. It's not strongly basic. It's more basic than Cl minus.
So the less stable one is the more basic one.
Correct.
In that case.
Yes. That's kind of the same thing over here. It's the same thing here. Which lone pair is more stable? The one in an sp3 or the one in an sp2? The one in sp2 is more stable. That's another reason you can say why this one's more basic. Okay? There could be multiple reasons that you could discuss. Which one's more basic, ammonia or water?
Ammonia.
Well, you memorized in Gen Chem maybe ammonia is a base, but why? Why is it more basic than ammonia? Yes, it's more basic. Why?
It's less stable.
What's your reason?
SP3.
They're both sp3, but the
Yes,
ammonia is less
hybridization,
stable.
they're both sp3 lone pairs.
But
The difference
oxygen
is
more or less.
electronegativity. Well, we're going across.
Oh, yeah.
You go across, electronegativity is more important. Which is more electronegative?
Oxygen.
Oxygen, so it holds its lone pairs tighter. Oxygen's a better parent. Nitrogen lets its lone pair get out there and react with protons. And it turns out that the nitrogen sp3 is actually a decent, pretty good base for being neutral. Now, I don't know if it's up here, but what if we compared ammonia to the anion, which is a stronger base? Hopefully this is very easy. Which one's stronger base? The anion. That anion is quite strong. I will hit on that in just a minute on the next page. Any questions about that page?
The one on the bottom.
There's one more at the bottom. Okay.
The most basic would be the one with the most.
What's the difference? Extra sp3 carbons which donate. Which one has the highest electron density?
The one on the left. Right.
Right.
Higher electron density because of the inductive donation of all these sp3 carbons is going to make this a stronger base. It would also make the anion less stable. How do you stabilize an anion? Pull electrons away from it, right? Well, this ain't pulling electrons away, it's donating compared to this guy. So this is less stable anion, and less stable is going to be more reactive in this discussion. Higher electron density. equilibrium of acid-base. If you haven't already done this, say hello to your neighbor, introduce yourself. See what's going on this weekend.
That should be easy. Everyone is learning.
Nice to meet you, sir. Left hand handshake.
Lab today, I won't be here for the first maybe up to an hour. Dr. Meow is going to fill in for me. I should be back by 3:30, maybe earlier, I'm not sure. Got to go to a high school graduation. Can't believe we graduated high school.
Are you meeting here still?
I didn't ask Dr. Meow. Probably not. He'll probably just get you going with limited discussion. So I think probably meet upstairs. 2:30. Dr. Meow will get you going with lab. Any questions about lab for you guys today?
Do we work in partners or by yourself?
Everything's by yourself except the last little bit when you do the miscibility with water. And there you can do with a partner. And because it's shorter, quick and sweet, and just to save on solvents, you can just do that with a partner. Otherwise, you want to work by yourself, because one of the main things with me in lab is for you to develop your independence, your confidence in lab. We will do one lab as sort of a group. Okay, predicting acid-base equilibrium. Reaction will favor the side with the weakest acid. Hopefully you covered such in Gen Chem. For example, back over here, we showed this on the previous page. I got it, I started getting into it, but I knew it was coming here. Acid-base reaction. Each side is going to have an acid. What's the acid on this side? Water. And we give a pKa for that acid. Okay? What's the acid on this side? Or you can call it the conjugate acid. But if you were over here and you went that way, then this would be the starting point. So it's, what's the acid over here? Do what? Oh, CH4. Methane. Okay? The acid is the thing that has the proton. Over the proton that gets exchanged. Over here, that's the proton. If we can put it in red, there it is. Where's it at over there now? Well, now it's one of these. Okay? So, that's the acid over here, that's the acid over there. You call that the conjugate acid of the base. And this is the conjugate base of the acid. Okay, equilibrium lies to the side with the weakest acid. Which acid is weaker, 16 or 40? 40, higher pKa, weaker. So the equilibrium is going to lie towards this side. So even though I drew arrows like this, it's really this side's favored. By how much? Of course, like all your calculations in Gen Chem, the difference is going to be, what, 24? 10 to the 24. What is that? Like 100 gazillion. Okay? So the equilibrium is sort of not like that, but more like this. Okay? Or even worse. It's pretty much complete. At equilibrium, you have 100 gazillion of these and only one of these. That's how you judge that. I know you did all those calculations in Gen Chem. Okay, down here, another example. That's a carboxylic acid. With one methyl, it's called acetic acid. You put this on your salad. Of course, you dilute it with water and you call it vinegar. Okay? And then you mix it with herbs and stuff and you make a nice salad dressing. Acetic acid has a pK of about 5. Put it in water, it will ionize. That is, water will act as a base. And it will take the H. And if water takes the H, it becomes this and leaves behind the conjugate base. pK of carboxylic acid is 5. By the way, in the back of your lab manual, there's a list of pKa's and some information there. Okay? What's the acid over here? Which species has the proton? Well, there it is. Water took it, it's now sitting here. pK of hydronium ion is less than 0. Which side's favored? 5 or less than 0?
Less than 0. I'm sorry, 5.
5, the weaker base. The weaker base has a higher pKa. This side is actually favored. That is, acetic acid, if you put it in water, doesn't completely ionize. Actually, more of it stays like this. What is the equilibrium? How much is this side favored? How did we get 10 to the 24? Did we say it's the difference in your pKa's? It's log 24. What's the difference down here? Well, if that's 0, the difference is 5, or greater if that's like -2. So this side's actually favored by 10 to the 5. And that's what? 100,000? 10 to the 5? So at equilibrium, you have 100,000 of these, and only 1 is ionized in water.
Is there any pKa's that you want us to know? Like obviously long.
At this point, you need to sort of learn them as we go along. By the end of organic 2, you have to have a good grasp. Water is 16. Also, your alcohol is 16. OH 16. Carboxylic acid is about 4 to 5. Those are probably 2 to kind of know at this point. The ones on the very first page where we showed HCl and acetic acid, there's like 4 or 5 there. Okay. Others are in that sheet in the lab manual, very back. Right before the periodic table, isn't there a list of pKa's? Back in the lab manual. But I also give you information of why the ranking is that way. Okay? Why the ranking is that way. All right, let's see how we do here. Okay. Show the result of this acid-base reaction. Predict which side is favored and by how much. Show the results of the reaction and then which side is favored by how much. Okay, what's the strongest acid on the board? Well, if we take this H off, we're going to go 2 minus. And you probably usually avoid 2 minus, 2 plus in organic chemistry. Also, you guys kind of just know that hydroxide is a base. Okay. So if that's the base, then this must be the acid. What's the most acidic H? The one on the nitrogen or the one on the carbons? Nitrogen. This guy. Okay. These electrons take the H, these electrons move on to the nitrogen, and we get the nitrogen now has, there's 1 lone pair there, right?
Yeah.
How many lone pairs now? 2, and that's a minus charge, if you can do charge, lo and behold. Plus what? What did we generate? We actually made water. Okay? To judge the equilibrium, you got to know the pKa of each side. The acid, pKa there I gave you is 8. What's the acid over here? Water. The proton's sitting here now. What's the pKa of water? 16. Which side's favored? 8 or 16? 16. By how much? Favored by 10 to the what? 8. What is that? 100 million? Yeah, because 10 to 9 would be a billion. 100 million. At equilibrium, you got 100 million of these anions, and only one remains. Question, is hydroxide strong enough to do this? Or is it just going to stay on this side? Yeah, it's strong enough. It's going to send it that way 100 million to 1. And if you turn that into a percent, that's what? 99.9999% is, yeah? Yeah, hydroxide is strong enough to be protonated this way. And you can form the nitrogen anion there. There you go. One's below. Let's do the next one. Same thing, do the next one. Then we'll need to get into the alkanes, cycloalkanes handout. Okay, what's the most acidic H on the board? Well, this only has CHs. The hydroxyl group. It's a phenol. Or is a CH more acidic? You'd rather make anion on oxygen than carbon. Yeah, there's the acid. So that's the base. Hey, that's reasonable because that's an sp3 nitrogen. Those are basic, tend to be basic. Okay, got the results shown? Good old mechanism. The base takes the H. If when you have something like this, like on a quiz, make sure you maybe show the bond in because I don't want to just show it in for you. But show it in, that way you can do the mechanism and you can move those electrons onto the oxygen. And what do we end up with? Oxygen with 3 lone pairs now, that's a minus charge. By the way, these are nitro groups. Nitro, that's a functional group. It's not on your list. It'll be introduced in organic 2. It's a common group on a benzene ring. You get that plus what? Nitrogen with, those are ethyl groups. You watching nomenclature? Ethyl groups. But what's here now? Nitrogen. Yeah, and what charge is that? That's not a typical. That's not a typical nitrogen. Yeah. There you go. Because guess what? It went from neutral to ion. Both of them. Both of these went from neutrals to ions. And you get that salt. With each ion being polyatomic complex. Okay, which side's favored? What's the acid over here? Thing to the H. Here's this pKa. What's the acid over here? Which thing has the H? That's the conjugate acid of the base. That's the acid over here. What's its pKa? pKa equals 10. told you very quick. Okay. This is a base. You ever heard of PKB?
Yeah.
I've never heard of PKB. Organic chemists don't use PKBs to describe a base. Organic chemists use pKa's to describe bases. But it's a base, not an acid. That's because the pKa of a base actually refers to what? It refers to the conjugate acid. Whenever you're given a pKa of a base, it's referring to the conjugate acid. What's the conjugate acid? That thing over there. So this pKa refers to the conjugate acid. All right? So, which is favored, 1 or 10? Which side is favored? The side with the weaker acid, which is 10. This side is favored by how much? 10 to the 9, what is that, a billion? Question. By the way, this is called triethylamine. Is triethylamine strong enough to deprotonate that phenol? Will it take it over here considerably? Yeah. I mean, 10 to the 9 is considerable. Okay, there's a couple more. I'll let you do those on your own. We'll look at them tomorrow, including this guy. The only difference here, the acid and the base are in the same molecule. Who cares? If you want to separate them and then do it, fine. And then rejoin them, it's the same thing. The acid and the base is in the same molecule.
What would be a not considerable number to make it go to the other side? Like 10 to the 1?
Yeah, 10 to the 1 would be just 10, right? That means in equilibrium you would have 1 on this side and 10 over here. Yes, it is favored, but in reality, in practice, you really want to have more like 10 to the 2, 10 to the 3. Or if it was 1 to 1, like this had the same pKa's on both sides, it usually just doesn't work out for you. Good question. Usually you want to have like 2 or 3 logs. Okay. Actually, before we move on, I want to make some good progress on the other handout today. This is important here. What about pH? Alkaline acid or base primarily exist at a certain pH. For example, a given compound. Cipro. How will it exist at pH of 10? What do you mean, how will it exist? There's 2 different possible forms for acid and the base. The neutral and the ion. Right? If it's an acid, the acid, and then the conjugate base. That's your 2 different forms. Which form will predominate at pH of 10? Or pH of 2? That's what we're talking about. How's it going to look? Basically, we're going to bring pH into it. Now, Henderson-Hasselbalch is an equation that kind of gets at this. And in biochem, you used to derive this. I'm not going to derive it, I'm just going to give it to you. Basically, it says that pH equals pKa plus log of B over A, where B is the basic species and A is the acidic species. This is your conjugate acid-base pair. The acidic species is when it has the proton. The basic species is when it does not have the proton. If you look at every reaction we did, on one side it had the proton, on the other side it didn't. Okay? We'll clarify that. Thus, you've got sort of 3 or even 4 unknowns. If you know this, this, and this, then you can solve for pH. Or if you know pH and pKa, which may be given to you, then you can solve for this, which is the ratio. But if the ratio is 1,000, you know it's 1,000 to 1, right? And you would say, hey, the B is predominant. That's why we're going to do it. Okay. Let's look at this B over A. if B is greater than A, if the basic species is predominant, it's more than A, then log of B over A will be positive. Thus, the pH will be greater than the pKa. If you can look at the numbers. On the other hand, if the acidic species is the major one, then log of B over A will be negative. And if this is negative, that means the pKa is greater than the pH. Right? If this is a negative number, like what? Negative 2? And if the pKa is 8, then what will pH equal? 8 minus 2? 6. If this is negative, the pH will be less than the pKa. Isn't that what, I think that's what was said there. That's the math. It's all just simple math there. But in summary, let's take home message. Here's the take home message. You ready for it? If pH is greater than pKa, B will predominate. If pH is less than pKa, A will predominate. Please go through the math, take the time, okay? I can't sit here because it's all these numbers and it's confusing unless you sit down and really want to understand it. There's your summary. Now let's do some examples. Here's acetic acid again. How will it exist at pH of 7, which is blood pH? If acetic acid was in your blood, how would it exist? Well, you got to know your reaction. That is, acetic acid is an acid. If it acts as an acid, it'll become the anion, the conjugate base, right? Something will take the H+. It'll, I won't say gives up the H+. Something took it. I'm not showing what took it, but it, okay? But these are your two forms. This is the A form, the acidic form, because it has the proton. This is the B form, because it does not have the proton. It's the basic form, the conjugate base. Okay? The pKa is 5. If we're at pH 7, which will predominate? Well, the pH is greater than pKa, right? Thus, which will predominate? B will predominate. At pH 7, B will predominate. It's all in the math. Look at your numbers. Everybody with me? Question? Okay, let me give you another way to look at this. This is a constant. pH can vary. I could have said pH of 2. I could have said pH of 10. I can't vary that. That's a constant for this. Here, the thing that can vary, is it on the basic side of 5 or the acidic side of 5?
Basic.
It's on the basic side, because a higher number is more basic. It's on the basic side. So guess what? The basic form will predominate. What if the pH was 2? Which will predominate? A will predominate. The acidics, because 2 is on the acidic side of the constant. A will predominate. In the end, A only predominates at pHs below 5. Above 5, B starts predominating. This is Henderson-Hasselbalch and understanding how something will exist at a given pH. Okay, there's probably questions somewhere in there. Other thing. We need to move on to the other handout there so we make some progress today. We'll see what's there tomorrow in the acid base. the question page has any of what we just did. It does, number 8, it's quite similar to the one we just did. It's probably something in the workbook though. Anderson Hoffman. Okay, you should have printed this yourself. Alkanes. Now we're going to start kind of focusing on more functional groups, types of compounds. We start with the most sort of generic, sort of hydrocarbon alkanes and also cycloalkanes. Test 2, we'll get into alkenes. And when we get into alkenes, there'll be a lot more reaction. Okay? With alkanes, we do have some structural considerations to look at. Rotation of the molecules. Conformations. Here's a warm-up page. You can look at some things. Types of questions you'll see. Nomenclature. Nomenclature by video. Any questions about the nomenclature? Covered that in the video. I don't think I worked this one in the video. Is that right? Everybody look and watch the video? Questions?
I didn't see on the sheet where you said how to name like double cyclohexanes.
Double what?
Double cyclohexanes.
Double cyclohexane?
Yeah, because you asked us to name this on the first page.
On the warm-up page of this handout,
Yeah.
that's just one cyclohexane. Why do you call it double?
Because sorry, the other one's benzene.
Yeah, the other is going to be a substituent on the cyclohexane, and I actually gave you the name of the substituent in the direction.
Right.
Oh, it's kind of complex, you wouldn't expect you to know it. Okay. Question?
Do you prefer one kind of naming over the other, like IUPAC or the?
Well, IUPAC is the official, and I ask for IUPAC on the test usually.
Okay.
What do you mean versus what common?
Yeah, the common, like the.
Yeah, you mean like these groups down here? You need to know IUPAC. Sometimes I would allow you to use common. You pretty much need to know these. But you often, usually, it'll ask you for IUPAC. Those are not IUPAC. Question?
On the second example, I know you named it on the video as right there, the 4,4 double or dimethyl.
Which one?
The second example.
Here?
Yes, sir. Just on the fourth carbon, so you named it as a 4,4 dimethyl.
What? Would this being one?
No.
1, 2, 3.
On the left side.
Oh, okay. I see now. 4. 1, 2, 3, 4. 1, 2. Okay. Which way? Come here because it'll give you 4, 4, 5.
Yes, sir.
The lowest substituents are there because you have 4, 4, 5 as opposed to 4, 5, 5.
I was wondering, like, say you had another methyl on the second carbon.
Here?
Yes, sir. Do you just keep combining all like?
You could combine it. You could call it a 2, 4, 4 trimethyl,
Okay.
with each number indicating where the 3 methyls are at.
Thank you.
Or if the other methyl was here, it'd be a 2, 4, 6 trimethyl. Yeah, you can do that. I want to hold off on naming the other one because I'm not certain that everybody's watched the video. I'd love to be wrong.
So,
Complex question?
so we should not go by these common name substituents.
Here,
Yeah.
if you ask for IUPAC, they're not IUPAC. Well, propyl is. Isopropyl is not IUPAC. This is really a 1-methyl ethyl.
1-methyl ethyl.
Yeah. Yeah.
So,
It's a 1-methyl ethyl. It'd be better if you have a question or is there a workbook question or something so we get more specific in the answer. Okay. Then your cycloalkanes are going to be just your rings, like this is a cyclobutane. It's an alkane that's in a ring. Most common is cyclohexane. Not necessarily most common, but it's the one we're going to be looking at. Okay, so let's move over to, I think we can pick up here. I don't think I did any of this in the video, no? All right. Condensed structures, we've alluded to this a little bit. Let's look at this in detail. Here's a structure. This guy here, this is not just pure formula. If it was, it would be C whatever, H whatever, O. It's sort of halfway between formula and structure. Closer to formula, but it's called a condensed structure. Okay? Where there's some information in it, but it's not drawn out full line bond Lewis structure. But we got to be able to decipher these. A lot of times parentheses are used. Also, a lot of times it looks like the H is bonded to 2 carbons, but it ain't. So you got to know what's going on here. So can we decipher this? I did the first one for you. What we have here is 2 methyls. 2 methyls on what? A carbon. Okay? So I got a carbon with 2 methyls. What else is on the carbon? Well, this H is there. I mean, you can draw it in if you want, but typically we don't draw them in, right? Then what's the carbon bonded to over here? The next carbon. And what's this carbon bonded to? 2 H's? Well, yes, it actually is, but it's also bonded to what?
Oxygen.
The oxygen. Okay? If we get rid of that H and don't draw it in, there you go, and that's what I drew up there. Question?
Do methyl groups tend to be in the ends? Like,
Yeah, I mean, because it only makes one bond. It's a CH3, right? I mean, it's only going to make one other bond, so it can't be in the middle. So, try the next one. You guys on my right, try this one. You guys over there on the left, try the third one. Together a full line bond structure. Okay, given the time, I decided let's look at those tomorrow, first thing, okay? Please have those. Those type of questions are there. Let's go down. Classification of carbon atoms by substitution. This is analogous to like primary, secondary, tertiary amines. You can also do this with carbon. Look at this alkane, okay? This is called a secondary carbon. Why? Because it's bonded to 2 carbons. This is called a primary carbon. Why? Because it's bonded to just 1 carbon. That's a tertiary carbon because it's bonded to 3. How about this guy? How many is it bonded to?
4.
Bonded to 4. That's called a quaternary carbon, or quaternary. But many people shorten that to just quat. Quat, usually with nitrogen. Nitrogen bonded to 4 carbons is often just called a quat, short for quaternary. Okay? Pretty straightforward. Same as this over here. That's a secondary amine because it's bonded to 2 carbons. It's a primary amide because the nitrogen is only bonded to 1 carbon. Now, but we can also classify the H's that are bonded to these carbons. So the H's on a primary carbon are going to be called primary hydrogens. H's on a tertiary carbon are going to be called a tertiary, like a tertiary CH. Of course, quaternary carbon don't have any H's. So there's no such thing as a quaternary CH. So that's the classification of H's. How many primary CHs in this compound? Well, remember, a primary CH is just an H's on a primary carbon. Please answer these, and there's no such thing as a quaternary CH, like we just said. Please answer these, we'll look at it first thing tomorrow. Okay, reactions of alkanes. Not much reactivity. Just sigma bonds, no lone pairs, not much reactivity. Except for you can burn them. And so anybody got a propane gas grill? Or, okay, you're burning propane. Or butane. Butane can react with oxygen. You give it a little spark or flame to get it going. What happens? All the carbon is converted to CO2, H is to water. And that's important. You generate heat. Heat your homes, you heat your hot dogs or your hamburgers or whatever. That's actually combustion. Now, this is probably a radical reaction. We're not going to look at the mechanism. It's common, okay? Probably a radical oxygenation. You can also do radical halogenation. This tends to be much more controlled. And you can maybe just put one bromine instead of multiple. Up here, you're putting multiple oxygens. You're also cleaving the carbon-carbon bonds. What's more controllable down here? H nu, this is light bromine. We can get this. This would be a substitution reaction because we're replacing the H with a bromine, substituting it. There's only like 5 or 6 types of reactions in chemistry, one being a substitution. In Gen Chem, sometimes you call it a displacement reaction. A substitution reaction. By the way, what type of carbon is the reaction occurring on? Primary, secondary, what? Tertiary? Yeah, occurring on the tertiary carbon. So we got some terminology we can use. I don't just have to point. I can say, hey, see the tertiary carbon getting brominated? Produce HBr. We may look at that. We likely will at the very end of the course. We'll come back to that reactivity. We won't look at the combustion. Okay. Overview of cycloalkanes. Let's introduce this today. We'll look at it a bit tomorrow. Of course, you can have lots of cycloalkanes. Even this, cyclopropane. Now, it is a pretty strain. From 9th grade geometry, we learned that this is like 60 degrees. So that carbon is sp3. It wants to be 109.5. So instead of 109.5, it's 60. And that's called ring strain. It causes the ring to have sort of a little high energy. Some students say, can you make such? Yeah. Cyclopropanes can be made. Actually quite common. Cipro has a cyclopropane. As you flip over, there's a variety of drugs that contain cyclopropane. The top 3 here, and that one does too. These 2 have cyclohexanes. Now the ring strain can be seen in your pizza formation. Heat of formation is the amount of heat that's released when you make a compound theoretically from the elements. The cyclopropane can theoretically, not practically, but carbon plus hydrogen to give that. Okay? Now, if you want to balance it, you can. It takes 3 carbons, right? I'm not good at balancing things, but usually when you start bonding, it's exothermic. And in larger rings, it's all exothermic. Negative kcal. This is like the delta H. It's a thermidor. But look at these numbers, positive. Why are they positive? That means making them doesn't give off heat or energy. It requires energy to make them. That's what these numbers mean. These can be determined in the lab. Why does it require heat to make those two small rings? Because they don't want to be made, because you've got to force them to meet the ring strain. Yeah. So that ring strain can be seen in these numbers. There's lots of other numbers here. Main important thing is what I just said, but also we need to start looking at heats of formation. And what does that really mean? What does a heat of formation tell you? Okay? And we're pushing time here. Probably I'll stop here, but let me just say some final things. We'll start introducing more about isomers. Okay? Including stereoisomers, different from constitutional isomers. We'll introduce that a little bit. Then we'll be getting into different projections, a way to look at the alkanes. We'll look at Newman projections, which I'll also call circle, circle, dot, dot. Okay, how to do those? I'll get out some models. I'll stand on the chair, or we'll do some things. Okay, more 3D. Energy levels. And I don't really have a lot of handouts about the last topic, but it'll be chair conformation. Bode and chair conformations, or cyclohexanes. So that's sort of where we're at. And this will be our last major topic before the test on Wednesday. Need to make good progress tomorrow, though. Again, Dr. Meow will be there in lab.